All right, so today we're going to do an example problem in chapter 9, and then I'm going to go over chapter 10. We have a lab this week, but I'm not going to assign it till Thursday. So, how's everybody doing? I hope you had an awesome break. I'm not sure if you got classes on Friday or not, but if you don't, then you had a break. If you do, you had a break on Friday. If you don't have classes on Friday, then you didn't have a break. Um, so you just had a regular weekend. Right. Thanks, Lawson. I always appreciate your interaction. Everybody else is a little, it takes a little longer for them to wake up for this evening course. But that's okay. When we start working on these problems, um, you'll wake up. But no, we're also well, I haven't come up with it yet, what the final project is going to be. Because the final project we did last year, I don't particularly want to do that one. So I'm going to come up with something different, and I will be assigning your final project probably next week sometime. And as mentioned before, you got an exam. It opens up tomorrow at 5, and you will have until Friday evening to complete it. The test is only 2 hours long, again. So once you start it, you have to finish it. If you don't finish it, you will get a 0. And if you start it and you email me and you say, Professor, some kind of way, I couldn't finish my exam. I started it. I didn't start it, but some kind of way it started on its own. You're going to get a 0. So don't email me. No, I'm just kidding. I'm just kidding. Maybe. So don't try me. I might be kidding. I might not be. I might just give you a 0. Um, but anywho, you have an exam this week. So I don't want to, overload you guys too much. So we will finish up chapter 10 on Thursday, and I will assign a lab. So that'll be pretty much it. But the problem, let's see, what problem do we want to work from chapter 9? Let's find a good one. I know you guys like the good problems, the juicy ones. Have y'all already finished this homework? What was it do? I might be done with this homework. Do I need to work a problem from chapter 10? I mean chapter 9?
I believe I did it.
You've done all of the problems?
Yes, sir. I believe so.
Oh, okay. Well, I don't know. We need to work any problems from chapter
Me,
9.
me and Cassandra worked on it together.
Oh, okay. Well, if y'all are done, then everybody should be done. So I don't think we need to work on any problems from chapter 9. Okay. All right. So everybody's done with chapter homework from chapter 9. We don't have to work on any problems. I don't need to go over anything.
Was that the homework that was due to test Friday?
No, this homework is due tomorrow.
Oh, well, yeah. Okay. Well, I have half that done anyway. So.
Oh, all right. Well, it's only 3 problems.
Yeah, I mean,
I was gonna help you guys out. Well, if y'all have it done, y'all don't need me then. I mean, y'all, what am I here for? You don't need me, huh? Oh, I thought you said something. We can work on the exam together. That's funny. Oh, thanks, Jacob. Yeah, we'll think about that one too. We'll work on it after you guys take it. All right, we'll work on it afterwards. So you guys go ahead and take it, and then we'll work on it after that. Well, all right. Well, let me just go over some things. I don't know if I went over because I know you don't have any problem uh, from it. this portion. Wait, that's chapter 7. Why are you there? Chapter 10. Yes, there is a review. I thought I sent that to you. I'll send it tonight. I'm gonna send it. Let me send it shortly. It may be because there is a let me see. Because there is a formula sheet. Yeah, so that is exam 1 review. Okay. All right. I gotta go find it and then I will forward it to you guys. I'll forward it. But yes, there is a review. All right. Let me go back over here. So today we're going to talk about force and how force relates to force-related variables in engineering. So this is like probably my second favorite chapter. And if you all have had physics, this should be pretty easy. If you haven't, then it's still going to be pretty easy. All right. I think we go over Newton's laws. So just to start you out, what are Newton's 3 laws? Gravity? Yeah. It's not wrong, but it has something to do with Newton's 3 laws. This is just a discussion starter. We're going to talk about it. Every action has an equal and opposite reaction. Yes, that's one of them. Which one is that one, Felicity? Yes, it is the third. That is the third. Correct, though. What's the first?
Isn't it like a force, an object in motion stays in motion?
Yep, something like that. Or if an object is at rest, it will remain at rest if there's no unbalanced forces.
Yes, sir.
Yep. Yep. And then there's one more. That was the first law. There it is. Force is equal to mass times acceleration. That is the second, y'all. There are the 3 laws. So what is a force? Well, it's the interaction of 2 bodies in direct contact or at a distance, like gravitational force, right? So it's just, think of it just that way, just the interaction of 2 objects acting on each other. So and then gravitational force is not an object necessarily, but it's like some gravitational pull. It's almost like a magnetic thing that's drawing us to the earth, to the ground. So it's what keeps us here on the earth, right? This gravitational pull is called a force. A force, obviously, is a vector, right? It has a magnitude and a direction. Tendencies of force. Natural tendency of a force acting on an object, if unbalanced, will be to translate the object, move it along, and rotate it, right? So it has to be unbalanced, so that there has to be a greater force acting on it in order for it to move. But if the force is not unbalanced, that's where Newton gets his first law. If that force is not unbalanced, then it would remain at rest, or if it's in motion already, like if it's moving at a constant velocity, it will just keep moving at that same velocity, like in space, right? If you've ever seen that movie Gravity, right, there was some flaws in it, right, in the theory and the motion behind it. I think there was one point where I think Sandra Bullock was flying, or somebody was flying, and then the other person went and just grabbed him. And I think that I don't remember the movie exactly, but I'm trying to vaguely remember it. But if I recall that how it was going, I think somebody was in motion, the other person was tethered, and then they flew out, or they kind of guided out, right? And they grabbed him. And as soon as they grabbed him, the person stopped. But that wouldn't actually be true, because though she was tethered, when she grabbed him, she would have basically started going in the same motion as he was going, and then she would have stopped, and he would have stopped after they got to the end of the tether. But what's actually also flawed in it, she would have never caught him unless she had some kind of propellant, and I don't recall her propelling herself to him, but maybe that's what happened. But anywho, if you are in space and you're moving at a constant velocity, you're not going to stop moving at that velocity, right? You're just going to keep going at that same velocity until some unbalanced force causes you to change your course or your direction. And so that's why astronauts have like a safer pack, right? But that's what's interesting too, right? You have this safer pack, and then once you jet yourself in that motion, right, you're going to just keep going in that motion. You have no brakes, right? You would have to have like another jetpack to kind of push you one way or the other, you know? But anywho, but that's a force. That was a force. And I think you should all know that just from being in physics. And then the units for force, obviously, is Newton. And what is a Newton? Newton is a mass. It's whatever. Well, if you look at the SI units, a Newton is the unit for force, and a Newton is a kilogram per second squared. Sorry, kilogram meter per second squared. All right. And so we've all talked about that. Another thing too is what's interesting when it comes to the U.S. customary units. Let me share my whiteboard. So if you look at 1 pound mass, right? And then if you're trying to convert it to 1 pound force, right, you're going to have to multiply it or divide by some gravitational constant. And so the way you would do that, you would go 1 pound mass times 32.2 feet, and this is gravity per second squared, and then you are divided by some gravitational constant, GC, which is equal to 32 32.2 feet per pound. Wait, feet. I'm sorry. It'd be 32.2 pound mass feet over pound force second squared. Some interesting constant, right? And then when you flip the second and multiply, right, which the only thing you gotta be flipping are these two. That would cancel with that. That would cancel with that. And that. And then what it ends up being is 1 pound force. I always found that interesting. I'm like, but just the whole concept, it's just interesting. Because 1 Newton is not equal to 1 kilogram. But that's neither here nor there, right? It's just an interesting concept. So if you're converting pound mass to pound force, that would be the process. But if you go from a kilogram to a Newton, you have to divide by 9.8 meters per second squared. I'm just interested. I'm just showing you that, but it's just so interesting that the U.S. customary units have this extra process that you would have to apply. And so if you were on a different planet, or if you were on Mars or wherever, then the gravitational pull obviously would change, right? And so maybe it would be 20 feet per second squared or something crazy. Right, and then you would have to, then it would be different. Pound force and pound mass would be different. But anyway, food for thought. Food for thought. So back to force. You have different types of force, right? You have wind, drag, viscous surface tension, normal forces, spring forces. We sort of talked about that the other day. It brings us to Hooke's law, where force is equal to the spring constant K times X, which is X is the deformation or deflection of the displacement of the spring. And so you all remember the other day when I talked about got some surface, some spring, and some mass, right? And then you have this constant K. And if it goes some force, and then you'll have like dotted mass changes. This spring, I should have did that differently. Right. So you go from where this was to where this is. There's some X. And so what ends up happening is you have this force here. Whatever that force is, we say is just a weight. And your K would be known based on that spring. You have your x, and then you can solve for x by dividing by the k, obviously. And so if you're looking for k, and your x is known, then you would divide by the x. And so you know that k is a Newton meter. Right? So, food for thought. But those are just different types of forces. Let's jump into this Newton's law. Well, one other thing. Then you have friction. Right? You have the friction force, which is not constant. All right. And so friction, and you have static friction that keeps things in place. And then you have kinetic friction that helps things to move. But in either case, you'll have some coefficient, and you will multiply that times the amount of force being applied to either keep you in place or help you to move. And so what ends up happening is your static friction, your kinetic friction has to overcome the static friction in order for you to move. And so these are things that if you've had physics, you know. If you haven't had physics, they're going to teach you. Because if there's a frictionless surface, then everything's in motion, right? It's just sliding. So like a glass floor, or, you know, if you go skating, or, you know, like the little hockey game, the air hockey game, the little thing, once you hit that thing, it just goes everywhere. You know, it's like a frictionless surface. Friction, it has friction, but it's so minimal. And a lot of that's because, you know, maybe dust particles collects on that thing, and it causes it to slow down. But initially, when they make it, it's possibly a frictionless surface. It's what they probably selling it to be. But dust particles float everywhere. It's hard to have like really truly a frictionless surface unless it's a slick surface, like if you pour some type of oil or put some type of soap on it, because like then right, or like magnetic tracks, because then the dust really doesn't matter. You have to put a whole bunch of dirt on the thing in order for something to stop, because otherwise you'll just keep slipping and sliding. But that would be more or less like there's no friction on it. So yeah. And then that brings us to Newton's first law, which an object that is in motion, or with a constant velocity, will continue to be in motion at that same velocity if there are no unbalanced forces acting on it, right? And so when you think about an unbalanced force, that's when it comes to Newton's second law, right? So for an unbalanced force, it's the sum of F, which is equal to mass times the acceleration, right? And so I always like to go to my board. You have the box, it's on the ground. At some mass, right? And so it's not going to go anywhere. It's just going to rest. I mean, there's this force from the ground being applied to the box, and there's this force from the box being applied to the ground, which that would be Newton's third law, equal and opposite forces. But the fact that there are no unbalanced forces on this box is going to remain at rest, right? But then if you place some unbalanced force on it, right, you add a force here. some type of a load, right, that is greater than the force being applied from the ground. And what happens, the box will start sinking into the ground, right? I know y'all just wanted to see my art skills. And if we know that load, then we can figure out. Right. Thanks, Lawson. See, he appreciates the artistry, right? He likes art appreciation. So do I. So do I. But anywho, if you know the if you know the load being applied from L, right? You sum the forces. Oh, not like that. I don't know what that was. You sum the forces, obviously in the y direction because we're only moving in the y direction. M times A. So what you would have is L, and say, so let's say this is positive. So it'd be negative L plus N, the normal force, right? And we equal to MA, which would be G in this case. And then if you wanted to say solve for N, then you would just add L, right? But seeing how it went through the ground and it stopped, if it stopped, right? And that would be what that normal force was on that box. But yeah, another thing to take into account is the A. Say we had a load on the box and it moved down at a certain acceleration, and we knew what A was. Then it would be mg plus ma. Oh, well, I know that didn't look right. Basically, you would add ma to this if we knew the acceleration of the box apart from gravity, in other words. But usually, whenever you'll see that that's going in the x direction. Typically, when you have constant acceleration, usually it's moving in the x direction. Which brings me to my next problem, which I'm not doing any problems. It's when you have like this slope, right? And you had a box on it, and then you have some force, and then you still have m, and then you know that this is at some angle. Then you would just solve for the moment for the force in the x and the y. And if we gave you the acceleration of the box, then you'll be able to solve for the force in the x direction. And then you'll be able to solve for the force in the y. Et voila. All right. Let's see if we got any examples we can do. So I know you all are just dying to work a problem. Let's look at example 10.5. 10.5. Example 10.5. Because we're going to talk about knock out two birds with one stone. So what you have is you have some force being applied. It's 50 newtons. You have another force being applied. 50 newtons. And you have another force being applied. And it's 50 newtons. And so the distance from here to here, 3 meters. We'll change it up a little bit. From here to here, 1 meter. And from here, 10 meters. All right. The angle is at 35 degrees. All right, now we want to sum up all of the forces in the X and then sum all the forces in the Y, right? What we're going to do, we're going to assume that it's massless. So what do we need to do to solve this problem? What equation is this again? So I've pretty much given you everything. I've just said you're going to need to sum the forces in the Y and then the sum the forces in the X. So you're just basically doing a sum problem. So obviously these forces are in the Y direction, right? But then this guy here is at an angle. So then it's going to be partially X and then partially in the Y. But if it did have, let's just say it does have some mass so that avoid any type of confusion. You have some mass there, right? Then that'll be the weight. So now, sum the forces in the X, sum the forces in the Y. So Y is going to be equal to MA, which is going to be G And then you sum the forces in the X. The MA. And so we like that Y is easy, right? So you just go 50, because we both know that this is positive. Y, X. So in the Y, we have 50 plus 50 is equal to mg, right? Or you can go 100 minus mg is equal to 0. That's it, right? And then you do that for the X. Now I'm gonna let y'all solve that part. The kicker is, how do you get, oh, we missed one, didn't we? Because this is in the X and the Y. So I'm gonna let y'all solve that part. How do we get the X and the Y from that particular force? You have to break out your trig, huh? You don't know. So we need, this is 50, right? So we want that guy. And then we want that guy. So what it would look like, I know that just looked horrible. I know y'all like, wait, what? What did you just do? Thanks, Z. I appreciate that. Yes, so many. It's gonna make sense maybe in a little bit. Maybe. All right. Try to make it a little bit more pristine, or rather lucid. Absolutely, it's a sine and cosine. So you have it this way, right? And so what you want is this way, right? And so you have that angle and you want it that way. And so you know the angle is 35. So opposite over hypotenuse is what? OPP, not other people's property, over HYP is sine, right? And so OPP dot, dot. So you would go 50 times sine 35 is equal to the force in D. Y direction. And then you would do the same thing for the X. Oh, wow. They got ugly too. What's the answer for the X and then the Y? So this is going to be plus 50 times sine 35. And that equals 50. Shit. What is it? Nobody. There it is. 28.60. All right. What is it in the X? $40.95 is equal to MA, or minus MA is equal to 0. Or whatever. So somebody got 40.95, somebody got 45.18. Do we have a third to break the tie? We have no third to break the tie. Nobody's going to break the tie. Oh, okay. So we'll just do an average. That's what we're going to do. Yeah, no, maybe. All right. So. Oh man, everybody's asleep. See, y'all talked last week. Now y'all don't want to talk this week. Y'all like, hey, everybody talked last week. We don't have to talk anymore. Like, I get it. I get it. Y'all punishing me. Y'all are punishing me. All right, Felicity got 40.95. Okay, cool. I got 40.95 as well. I got 40.95 as well. So that's what we're gonna go with. And there it is. So, but if you look at this problem in your book, there's something else going on here, right? There's this momentum happening. Right, there's this momentum happening. And what is momentum? I was trying to delete all that, but it was just like, I don't know. It's not letting me do it. Let's see if I can do it quick. No, it won't let me do it. Whatever. So what is momentum? Anybody? Not momentum, a moment rather. There's a moment happening here. Yes, a moment has magnitude and direction as well. It's like torque. Is this force rotating or causing an object to bend or rotate, right? And so the moment is the force at a distance of that's creating the rotation or the twisting, right? So when a force is applied to an object, it'll create some type of a bending moment, right? And yes, that force in that moment, it is a vector because it could be bending in different directions, all within the same object. It could be twisting as well, like torque. And I think that was Mason who brought up that the torque, right? It's force times distance. Wherein a distributed load that we were looking at is force over distance. That's kind of like the spring constant, right? It's like a spring constant that's changing over the distance, while torque is increasing times the distance, right? So in that problem, we had a torque happening, a moment happening. And so when you go back to my board, we won't do that whole problem because it just takes forever. See how long it took us to do that. And then y'all aren't talking. So like, man, our throat hurts from all of that talking from last week. Sore. We're sore, teach. Our vocal cords is sore, teach. I'm the teach. Y'all are telling me that. That's what y'all are telling me. Throat sore, teach. I know I'm silly. Right, so there's a force being applied and at a distance D is applied at point B, and so this is point A, and then you have some type of deflection, but that's an and or figure eight. That's not what I was trying to draw. Trying to draw a delta sign. I don't think I remember how to do it. It's something like that. I don't remember. Whatever. We'll just say X. All right. So what ends up happening is you take the moment about A, sum the moment about A. What ends up happening is you will take the force F at point B times the distance D. And that'll give you the moment about point A, right? And if you was trying to figure out the deflection, then you would have to use some other equation to figure out that deflection. You have to do some integrals actually and figure out the change in distance, the change in X over that moment. But we're not gonna do that. I'm not gonna have you do calculus in here, so you don't have to worry about that. Does everybody get that? So I'm just gonna draw it so you have like a cantilever beam. Right, and then there's this A here. So if you all have statics, you all know where, right. If you all have static, you all know where I'm going with this. And so this is A, and then it's at a length L, right? And then so what happens is you got this is a force F. You got like some reactions happening here, but then you have some moment occurring. And so say the moment here is positive, and then this moment is negative. And then if you had another little load here, and then it's at L over 2 or some distance A. What do we need to do to solve this problem? I just told you. Well, since you guys didn't talk, now you have to solve it. So what do we do to solve this problem? We wanted to find this load L and then this load F. Force times distance, absolutely. So what do we need to do? We do the sum of the moment about A, right? I'm not sure what that noise was. It's coming from the other room. But anywho, so force about A, possibly it was. And so you would have F times L, right? L, and then you got L times A. Now, the question is, what direction is it going in? Now, how many of you know the thumb rule, the right thumb rule thingy? So what they say do, you're supposed to like put your thumb in the direction of the force and then curl your hand to the point where the thing is occurring, or right, something like that. That sounded funny. So you put your right thumb down in the direction of the force, right? And then you curl in the direction of the point that you're taking a moment about, if that makes sense. Does that make sense? I thought we had pictures in here of the right hand rule or right thumb rule or whatever. Yeah. Yeah, I know, right? Let's see. Let me break out. So y'all haven't had statics yet. So Chelsea learned it in physics. All right, do a demonstration, Chelsea. So just come off of, just put yourself on video and show everybody how to do that right thumb rule, since you learned it in physics. I'm just kidding. I'm just playing. I'm just playing. I'm only kidding, Chelsea. You don't have to do it. Right? That was funny. Y'all know me by now. I like the kid. I like to kid around. I would never make anybody come on video to do any type of demonstration. That would be horrible of me. Yeah, you're supposed to say you don't know. You're right, Jacob. You're supposed to be like, but they say not me, I ain't it, or something like that crazy. All right, I'm gonna come off and try to show y'all, but man, it's what's crazy about it, man. It's like it's so awkward when I do it. It looks funny. Now I don't have any makeup on, and I haven't, I haven't done my hair, so excuse the look. When y'all see me, I don't have my makeup on. I haven't done my hair either, so I don't wear makeup. I'm just kidding. I'm an idiot. So I can you all see me? See my hands? Jacob said the same. Yeah, I don't wear makeup. I'm only kidding on the makeup thing. All right, cool. So the right hand rule, the sense, i.e., the direction of the moment, is determined from the right hand rule, right? So the right hand rule, place the position and force vectors tail to tail, right? So you got the position, right? Say this was your moment line. And then say this was your force line. And then this was your position line. Right? That looks horrible. So let's look at it in this case. So this is your force line, right? And then you have your position. All right, so you got your position, like this is A. Just excuse the drawing, it's just gonna look horrible. That's A, right? This is your, basically this here, bending. So it's bending this way. All right. And then your force, right? This is your force. It's going down. Right. And so we would put our force here too. Right. So we're placing it basically tail to tail. All right. And then we have a moment. Say we put the moment somewhere. Let's say we did it here. All right, we did it here. Let's just do it there. So what it says do is like you so that our moment line is going that way, right? That's the way our moment line is going. And then it tells you to curl. Rotate the position vector into the force. All right, so basically your position vector, it would be going basically back this way. I know y'all are geeking right now, man. I'm glad I can't hear you. So this is your moment. This is your position line here. And then your force is there. So you go bam, and you rotate that thing that way. Bam, bam. So what way is that? I'm going back this way. So that's clockwise, right? Bam, it's clockwise. So you go bam, got the moment, the position. So we just do it this way. You got your moment, you got your position, and you go this way. So like a back slap. Flap. And so it basically I went this way, right? And so that's clockwise. And so I said clockwise was positive. So that would be positive. All right. So we did the same thing for L, right? It's going in the same direction. The deflection's in the same direction. So then that would be clockwise as well. So this would be a plus. All right. Signing off. Did that make sense? More sense? Maybe? No, not really. If not, I don't know what to tell you. Z said no. Yes, no, it didn't. Yes, no, yes, no. There you go. Just look up videos later. I love it. There you go. And if it makes more sense, because I just said thanks for trying. Ah man. Well, say I tell y'all what. What we'll do next time is we'll just do a YouTube video on it all together. How about that? All right. Great. I did my best. You know what I'm saying? Y'all had me out here looking like a clown, and I'm recording this, right? And so people gonna come on there and look at me like, what was he doing with his hand? Did he say he backslapped somebody? Right? So it's all in fun. I'm glad you got to laugh about it. Well, at least I laughed. I thought it was pretty funny. It's just back slap, just backhand slap. That's it. Just do a blip, blip, and then you say, "Oh yeah, that's positive." And then if you do a forward slap, that's negative. So you slap them from forward. That's negative. Back slap, that's positive. That's all you need to know. Forward slap, negative. Back slap, positive. So it's positive to do a back slap on somebody. That's positive. That's a good thing, in other words. I'm just kidding. I am just kidding, guys. I'm gonna have to delete the footage. He said, slow down. Jacob, do not write that down. Rick, you're funny too. You understand now. Good. Hey, as long as you understand, I've achieved my goal. She said she got it in her journal. Forward slap, positive. Back slap, positive. Forward slap. All right, good. Glad you got it. I'm glad I can help. I'm glad I can be of service. Moving right along. It's always something during my classes, right? It's just, hey man, at least you're gonna get entertained kind of when you come. So yeah. All right, moving right along. That's a moment. Yeah, what else we got? Next we have work. Work, obviously, and moment is the same thing. So when you're looking at a moment, you're like, so what was happening was work was being applied. But yeah, it was. But just in a different form, right? Because it's weird. You calculate them the same way, but you don't look at them as being the same. Just like torque in a moment. Like the torque is different from a moment, but they're all calculated the same way. So work is just force times distance. And then power is work over time. All right. And then pressure, we all know that one, force over the area, the surface area of a material. And these are the different units of that, of which we've discussed. You can also solve pressure from density times gravity times height. And then you have buoyancy force. And the buoyancy force is the magnitude of the buoyancy force is equal to the weight of the volume of the fluid displaced. All right. Weight of the volume of the fluid displaced. And then you have atmospheric pressure, you got gauge pressure, and then you have absolute pressure. Atmospheric pressure. I'm not going to read all of that, but just keep in mind. One thing to notice too, when you think about gauge pressure like your tire pressure, and then your absolute pressure is your atmospheric pressure plus your gauge pressure, right? And so at a certain temperature, we've always take into account that atmospheric pressure is 14.7 psi. That's your atmospheric pressure. And I think that changes with elevation. Right, and so 14.7, yeah. So at sea level, I believe atmospheric pressure is like 14.7 psi. And now if you're in Denver in the mountains, that changes, your elevation changes, so your atmospheric pressure will be different. Just something to keep in mind. I think that was what we were saying here, the weight of the column of air. Mount Everest. Yeah, so at Mount Everest, your atmospheric pressure is approximately 30% of the atmospheric pressure at sea level, approximately 38% of the air density at sea level. So this is your atmospheric pressure on Mount Everest. All right. Stress, same units as pressure, force over the area. Then you have the second moment of area. Remember when we talked about that? Moment of inertia, second moment of the area. Now, that's really key when you're looking at momentum, right? So when you think about momentum, you think about moment of inertia. And that's also in chapter 9. So let me go over. So I want to go. I know I'm jumping around, but I want to touch base on this. So the mass moment of inertia, it provides a measure of how hard it is to rotate something in respect to the center of rotation. And so simply means this. So you have a pendulum, all right? And for a single particle m located at a distance r from some point that it is like if it's attached to something or if it's nailed to something and you have it swinging from this point, you got a mass at a distance from that point. And then your mass moment of inertia is basically the resistance of that. It's what's causing that resistance. Or as they said it, just to put it back in those terms, it is provides a measure of how hard it is to rotate that ball from a pendulum. So when you think about the bending moment, and I know you're like, oh, hey, you're just saying too much. But when you think about a bending moment, right, of say a balcony, right? Like if you have a load being applied to that balcony, the mass moment of inertia will help provide how thick that thing should be to keep it from breaking or bending beyond, like the balcony, that is, the balcony being bending beyond the point of returnability, in other words. And so what I mean by returnability is returning back to its initial state or form after the load was applied to it, right? And so you want it to be basically rigid. So if you're going stepping out on your balcony, if you have a balcony at your house or at your apartment, and you step out on your balcony, well, they determine how thick that balcony should be using this formula, the mass moment of inertia. And one thing to keep in mind is your mass moment of inertia will change based on the shape of the thing, right? And so you would use this for a balcony, right? Because it's in the shape of a square. So, and then you would use this one for the sphere, just like the little ball on a pendulum. So, yeah. Any questions on that? Nope. All right. Back to 10. We're almost done. I think we are done. I think that was it. I think that's all I wanted to share. So on Thursday, we're going to work a couple problems. Yeah, that's all I want to cover. We'll talk about modular elasticity and modulus of rigidity next week. On Thursday. Sorry, we'll talk about that on Thursday. So, any questions on anything? Labs, anything? All right, cool. If there are no further questions, Your Honor, you are free to go.